Hey guys, so today we're looking at the two-sum problem on LeetCode. The problem statement is, given an array of integers, return the indices of the two numbers that add up to the specific target. So in this example, they're giving us the numbers 2, 7, 11, and 15. The target is 9, and the two numbers that add up to 9 are 2 and 7, which are at indexes 0 and 1. So we're expected to return 0, 1. So how would we write an algorithm to solve this problem? So we're given the array 1, 3, 5, 8. And we're looking for the number target is 8. And we can't just use 8. We have to find a pair. We can use two iterators to do this. I and j, and just for clarity purposes, I'll number these indexes. So this is index 0, index 1, index 2, and index 3. And this is a naive or brute force implementation. So this would be if you're nervous in your interview and you can't think of the optimal solution, you just start solving it, even if it's in, for lack of a better word, a stupid way. This problem is technically an easy problem, but first time I saw a problem like this, it was really hard. I didn't even come up with the brute force solution. I was just nervous, and maybe the easy ones are easy for you. So, and if they're not, don't feel bad. So the naive solution is we're going to have two iterators, and we're going to start them both at 0. So I is pointed here, and j is also going to start at 0, and j is pointed here. And in the next step of the algorithm, we're going to increment the inner loop. And so now j is pointed here, and then we're going to increment it. So we've incremented j, and so now j is pointed here. And notice I is still pointed here at index 0. We haven't touched that yet. Increment j again. So j is pointed here. Now after j reaches the end of the list, that's when we reset it and increment I. So reset it and increment I. So the inner loop exits, and we get to the next iteration of the outer loop. And so I is no longer pointed here. It's pointed here. So here's I, and here's j. So we loop through every possible combination. So for the naive solution, we'll have for let I equals 0, I is less than nums dot length, non-inclusive, I plus plus, and we'll also have an inner loop with j, and j less than nums length, non-inclusive, j plus plus, and we're going to say if nums I plus nums j is equal to the target, then we found the solution. So we would just return I and j, the two indices we're currently considering. And in this manner, it just loops through and does an n-squared solution, loops through every possible candidate for the first number in the pair, and loops through every possible candidate number for the second number in the pair. So there's n-squared comparisons. It'll try every solution in the worst case. It'll try every possible combination, n-squared. And so that's not super efficient. For one, I and j could both be pointed to the same number. And as it said in the problem, you have to have a pair of numbers. You can't just use the same number. You can't just use a number once. You can't use a number more than once. So we're doing all these loops, and then we'd have to check if I is equal to j, if both pointers point to the same index. That's not even a valid solution to consider, but we're still like looping over all of those and checking if we're in that case, which takes up time. And so a refinement on this would be to basically, you have your I equals 0, and then you have your j be I plus 1. So that's the first comparison that you would make. So I is here, and j is here. So we're eliminating that bad comparison in the naive solution where we're comparing the element at index 0 to itself. Then you basically, here, let me draw this out in a shorthand way. You iterate j all the way up until the end, just like with the first solution. So we go all the way up to the last index, which is 3. Then it resets, or the loop exits rather, and we come back up here to the outer loop. We increment that, and then when we get back into this inner loop, we set j to I plus 1 again. So this time it goes to 2. And so now I is right here, and j is at here. And so we specifically skipped comparing this way. And whereas before we had like a n squared solution, now we have like an n triangle kind of solution, where basically we're comparing 1 to 3, 1 to 5, and 1 to 8. Then we're comparing 3 to 5 and 3 to 8. Then we're comparing 5 to 8. Whereas before we were doing like this, 1, 3, 5, 8. We compared 1 to itself, and we compared it there, and we compared it there, and compared it there. And then when we were at the 3, we compared that way. We compared 3 to itself. We did every single possible comparison. So the optimization we can make with this is initializing j to I plus 1, which is very easy to do. We just initialize right there to I plus 1 to prevent ourselves from making unnecessary comparisons. It's just tricky to realize that you can do that until you work through the problem, and that's why I always recommend working through a problem on a pen and paper or a whiteboard. So let's just say I is 0, which means I is pointed here. So we're considering the number 1. What number plus 1 equals 8? Well, that'd be 8 minus 1, which is 7. And so what we could do is in a hash map, we'll say what we can do is store that information in a hash map. And in our hash map, we'll say, if you see a 7 later on, its pair is at index 0. And then we increment I. And then for 3, is 3 in the hash map? No, we only have a 7 in the hash map. So what number plus 3 equals 8? Well, that would be 5. So we're going to store that information in the hash map. We'll say if you see a 5 later, its constituent pair is at 1, index 1. And then we increment. So I is pointed here. And is 5 in the hash map? Yes, it is in the hash map. Right here, 5. We said if you saw a 5, its constituent pair is at 1. Well, we did see a 5, which is at index 2. And so the answer is going to be the numbers at indexes 2 and 1. And so in this manner, we could do it with only one loop in linear time. So we, in the worst case, go through here and populate the hash map and then determine that there is no answer. So let's get to coding this. So we're going to have a hash map. I'm just going to use a JavaScript object for this. And we're going to say for let I equals 0, I is less than nums.length, non-inclusive, I++. And we're going to subtract the current number from the target. And that's going to be the diff. And we're going to put that diff in the hash map so that if we see a number that's the difference later on, that'll be the answer. And then prior to doing that, we need to check the number that we're currently considering. So if the hash map has the number we're currently considering, then that's the answer. I'm going to say if undefined is not equal to the number, then we have our answer. And that is how you do the to-sum problem on LeetCode. Thank you.